Hello again, Regents students, to our second lab video. This one is called Adding Forces. Once again, your lab partner is me. By this point, you should have printed out, if you are able, the lab sheets that are in the Google Classroom stream. I should have mentioned this during the Pi Lab. The two first pages, which are the instructions, you really don't have to print those out. You can obviously look at those on a screen and read the instructions. The paper part that you're going to fill out would be great if you could print it out. Otherwise, you're going to have to try and recreate this on a blank piece of paper with a ruler and a pen or pencil. And that's going to be time consuming. So hopefully you're able to print at home. Okay, so now before I jump into the science of the lab and the materials, I want to point out the educational purpose of this lab is that you can add forces graphically. Adding forces graphically, as I mentioned in the lessons, is not using the Pythagorean theorem, not using the sine, cosine, tangent functions. It is drawing things with a paper, a ruler, and a pencil as accurately as you can and getting the answer from measuring the resultant force, constructing a parallelogram, measuring the diagonal, and using ratios to figure out your answer in newtons. So that's the point, what you're going to be graded on. You should not be using the Pythagorean theorem anywhere in this lab. It's all drawing arrows accurately. Now, if you don't have a ruler at home, also I would like to say I have included an image of a ruler on Google Classroom Stream. Hopefully you can print that out at home. And then you can cut out the ruler and use that to make your measurements. When you're submitting your lab with photos, I want you to have the ruler somewhere in the photograph, because the only way I will be able to check the accuracy of your drawings is by looking at how big is a centimeter in your photograph and comparing that to your vectors, your arrows that you've drawn. So those are the basics about what you're going to be graded on. Hopefully that's clear. If you have any questions, then obviously let me know and I'll try and answer them as best as I can. So let's now jump into the science behind the lab, what we're going to do, the equipment we have. So once again, I'm reading off the lab sheet here. For the scientific purpose of this lab, the purpose of this lab is to add forces graphically, drawing arrows on pieces of paper. That's what graphically means. So the equipment that I'm going to be using to achieve this purpose is a wood board, a string, okay, a mass set, an extra 500-gram mass, a spring scale. I talked about these in class, right? They measure force in newtons. A protractor, a C-clamp, 2 pulleys, okay, and that's it. So the first part of the procedure, step 1, says clamp the board to the table using the C-clamp. The diagram below, use the diagram below and the model in the front of the room to guide you. So I'm going to do that for you, obviously. I'm going to take this board, I'm going to put it on the edge of the table, not like this. I'm going to have it hanging off the edge of the table, okay, on both sides. There's a gap here and a gap here. And then I'm going to take this clamp and just, maybe I'll do it this way. All right, this tighten, and now the board is secured to the table. The next thing I'm going to do is I'm going to put the pulleys on these lines here, but these are made of plastic. Hopefully we're back in school later in the year. We'll be using these pulleys again later in the year. And I will tell you now, and I'll tell you again when you hopefully use them, you don't tighten these very tightly because they're made of plastic and they just snap if you tighten the screw too hard. Okay. All right. There, free to turn. Okay. Next, step 3, hang the 500-gram mass on your spring scale. Record the force it exerts in your data sheet. So, first thing you have to do with the spring scale is you have to make sure it reads 0 when there's nothing on it. And right now, you can see that that's not the case. This little pin is reading somewhere around ½ of a Newton on this side. So to fix that, the metal slides around and you move it till it reads 0 with 0 load on it. So there it is. I've zeroed the spring scale. And I'm going to take 500 grams of mass, which I could use this block here, or 500 grams off the mass set. It doesn't matter. They're both 500 grams. I hook this on, and then I register the reading in newtons on this side of the scale, and I get around 4.9 newtons. Again, don't jot this down. I will basically give everyone data on a spreadsheet. So 4.9 newtons for the 500 grams, I'm filling that in. Again, you're getting that number off of a spreadsheet. And then the next step 4 in the procedure here, okay, it says hang 300 grams on your spring scale. Record the force it exerts on your data sheet. So I achieve 300 by taking the 200 gram mass and the 100 gram mass. I could either hook them both on the spring scale or hook them in a chain like this. This is now 300 grams. I hook this again to the spring scale and I make my measurement carefully. This looks, I'm going to say, 3.0 newtons on the dot. Okay, so I'll fill that in. Okay. Now, step 5 says hang 500 grams off in the y direction. So the y direction is here, and then 300 grams off in the x direction. That's this way, x and y. Okay, so this is going to be a little tricky by myself. With a lab partner, you have an extra set of hands, but 300 grams off in the x direction will be here. I'm just going to put this not on the pulley yet because otherwise it'll just fall off. So, and then 500 grams over on this side. So you see I got the 500 gram here, and I'm going to put it off of this pulley. Now, and then I'm going to hook this on here eventually to measure the resultant of these two forces. So what I'm going to do is just hold this knot right like this, and I'm going to put this 500 grams on the pulley right here, stop it from swinging, and then 300 grams over on the x side. And then what I'm going to do is I'm going to measure these two forces combining at this knot with this spring scale. And that'll give me the resultant of those two forces. Oops, fell off. All right, now here, if we were doing this lab, I would tell you to be careful because what I have to do is get the pressure off my finger using only the spring scale, but you can't do stuff like this, twisting the spring scale, because then it doesn't work accurately to measure. What you have to do is you have to just put your finger through here and allow the spring scale to just sort of swivel to freely so that it's truly measuring the combined forces of these two. Then I move this spring scale around and you see the knot moves around. We want to make sure the knot is hovering right over the origin of the board, and then that will give us the accurate addition of the 4.9 newtons here, that's the 500 grams, plus the 3.0 newtons, that's the 300 grams. And I read, for a spring scale reading, about 5.6 newtons. I'm going to write that on my sheet here in box number 7, the resultant. I think I said 5.7 is going to go right there. And then I'm going to measure the angle. There's a spot here for the angle as well, by putting the protractor at the origin of the board and then seeing what angle the string makes to one of the axes. and I'm standing directly overhead, and I see that I'm looking at about, I think, 32 degrees, this string hitting the protractor. Okay, so that's 32 degrees, 5.7 newtons. I'm going to jot those down now. Okay, so I do this so that the whole setup doesn't fall when I let it go. 5.7 newtons and 32 degrees. Once again, you want to make sure that you're getting your data off the spreadsheet, but when you do get your data, I don't know if you could read this. Maybe I'll do this, get a little closer, okay? So what you want to do is make sure that whatever your number is here, you label a unit of newtons, okay? Same here, 3.0 newtons. In Regents, the units are very important. As I might have already mentioned in the lessons, I'll certainly mention it all year. You lose a lot of points if you don't put those little n's, those little newtons. Same here, 5.7 newtons. And the angle is not 32. That degree symbol on the Regents test, you don't put that on, and it'll cost you dearly, that little degree, that trivial little symbol. So I have the data for the first trial. Okay, so hopefully you could see the sheet here. Now what I have to do in step 9 and 10, step 9 says in the procedure, in the calculations, convert your measured Fy to centimeter lengths using the scale of 1.4 newtons to 1 centimeter. This is worth 2 points, ratio with units and answer with units. So first point will be setting up the ratio, the second will be for your answer. So remember, you need units everywhere, so this is how I would do that. I would start with, as I mentioned in class, my ratio of 1 centimeter to 1.4 newtons. Okay? Now, on the other side, I'm going to have my centimeters and my newtons. So on the top, I have centimeters for my Fy, which I don't know. So what I'll just do is I'll label that with a variable of Fy, or you could just use Y if you want. And then down here, my force in the Y direction is 4.9 newtons. So that's 1 point. Missing the newton or centimeter, any one of those units, you lose a point. So I cross multiply 1.4 times F, 1 times 4.9. In this step, you don't need the units. The Regents only in the setup and then in the answer. What I'm going to do algebraically is obviously divide both sides by 1.4. So I'll take my calculator and I'll do 4.9 divided by 1.4, which is 3.5 centimeters. So that's my Fy for my measurement. Again, right now I'm thinking I'm going to have everyone have their own data, so you're going to have different numbers here. But the ratio and how you set it up will be the same. So that's 3.5 centimeters. I label that as well. I repeat on this side with the same ratio, the same conversion factor, but this time my x-coordinate is 3 newtons. So how long is that in centimeters? I will use the ratio again. Centimeters over newtons, cross multiply 1.4 times F, x equals 3. Divide both sides by 1.4, so I'll do 3 divided by 1.4, and I get 2.14 centimeters for Fx. Okay, so the next thing that I'm going to do is now I'm going to draw these two forces on the chart provided here. So in the x direction, you can't see it, but it was 2.14 centimeters right here, 2.14. So in the x direction, I'm going to get a ruler, and I'm going to try and be as accurate as I can 2.14 centimeters. So I draw a line, something like this, 2.14, something like that. There's an accurate line, 2.14 centimeters in the x direction. Remember, don't draw a sloppy arrowhead like this. Be as precise as you can. Put your pencil very carefully on the end of that line and pull back to make your arrowhead. Without arrowheads, Regents doesn't give you credit. Okay, so now in the y direction, I'm going to draw 3.5 centimeters. So I'll put my ruler right here and go up in the y direction as accurately as I can, exactly 3.5 centimeters. Okay, so there's my line, 3.5 centimeters. Again, no sloppy arrowheads. As precisely as you can, put your pen or pencil right on that end and go back. I would recommend a pencil, by the way, because you may mess up and you may have to erase. And then if you can't erase, it gets pretty messy. To add these forces, remember, you've got to make a parallelogram. So we, as accurately as we can, we make some light dotted lines like this, which actually it turns out to be a rectangle in this case because of the 90-degree angles. And another. Okay, so that's crossing there. Now, that takes me to step here, construct the proper resultant and label it R. So that's another thing the Regents likes. Oh, I should have labeled these, by the way. Fx and Fy. And then I make a nice, precise arrowhead along the diagonal. That is the sum of those two forces that I had on the pulley, represented graphically. So again, I make as precise an arrowhead as I can, and there we are. I got a little sloppy there. Let's erase that little tip on that arrowhead. Okay, so now we are on step 13, I think. Measure the magnitude of the resultant in centimeters and convert it from centimeters to newtons using the appropriate scale. Okay, again, 2 points. So you got to set up a ratio again. So, oh, I forgot, label it R, right? Regents likes those labels R. Or you could label it FNet as well. That's acceptable, that is correct. So I measure this now as accurately as I can, so you're going to be graded on how accurately not only you draw, but how accurately you measure. And I see about 3.12 centimeters. So 3.12 centimeters, or was it, no, 4.12, sorry. 4.12 centimeters. So now I'm going to use my same ratio, 1 centimeter to 1.4 newtons equals, now I know it's 4.12, I think I said. 4.12, yeah. Centimeters. Oops. Yeah. And then over how many newtons? I'm going to label that R because I don't know the newtons, right? I know how many centimeters, but I want to know how many newtons now. So I cross multiply. 1 times R is R. And then 1.4 times 4.12, I use my calculator. 1.4 times 4.12 equals, I'll round that to 5.77 newtons. And then lastly, step 14, calculate the percent error. Consider the magnitude from step 13, the accepted value, and the value from step 7, the experimental value. With the spring scale, step 7, I got 5.7. Step 13, with the drawing, I got 5.77. So now I will do a percent error. Here you don't have to do a formula because I didn't leave much space. So maybe I'll just write percent error. What it is the accepted value, first of all, absolute value, the accepted value minus the measured value, the spring scale value, 5.7 newtons, all over the accepted value right here, the 5.77, times 100%. So let me do that. 5.77 minus, well, I'll do parentheses. 5.77 minus 5.7, oops, this minus 5.7 divided by 5.77. Now I take that answer and I multiply by 100%. And I get 1.2%. Very good for this experiment. So that's how you do the calculations. So again, you're going to have your own numbers. But again, the key points are units in all these measurements, a ratio with units everywhere except for the variable, and then an answer with units and on both sides. And then the drawing here, the arrows as accurately as you can. I'm going to be checking that. Construct the resultant after making some dotted lines, measure the resultants, and use the ratio again to calculate the resultant here in newtons, and then do a percent error. Okay, so now we are on step 15 here. It says repeat the entire procedure, but replace the 300 gram on the FX pulley with a 500. So I'm going to leave 500 here in the Y direction. I'm going to take this 300 and replace it with a 500. I could use this metal block. It's also 500. So what I need to do is, again, measure the forces. This was 5.7 newtons. So I can just transfer that as my Y force here, 5.7 newtons, writing upside down. Hopefully I get it right and legible. So there's 5.7 newtons. And this should be 5.7 newtons also, but you know, the metal might be chipped or rusted away, so I will measure it anyways. And I got it on the spring scale here. I'm going to pick it up so I could see it more clearly. Oh, this one's only about 4.8 newtons. So this one is 4.8 newtons. Oh, wait, not 5.7, 4.9. 4.9. I copied the wrong thing down here. 4.9. And this is 4.8. Again, you'll get your own data pieces here from the spreadsheet that I'm going to attach to Google Classroom. Okay, so recall that what I want to do is get these to add through the string, and I can measure then with the spring scale what the combined forces are of 4.9 and 4.8 newtons. So I have to get this sort of awkward string set up to get into equilibrium again. 500 grams off this way. I'll temporarily put this like this, and this metal block here. Okay, so let me hook this on the spring scale. Hopefully it stays on this time. Okay, let's see. So now I've got to get these two strings to be on these low friction pulleys so we get a nice efficient adding of forces. I lost the string. Okay. Again, I want to just put my finger through this and let the spring scale sort of freely swivel to whatever angle it needs to be, but I can move this around until I achieve equilibrium, and I could take the pressure off this finger, and the knot is freely held, or I should say held only in place by the spring scale. So now I am adding this 4.9 newtons in the y direction, 4.8 in the x direction, and that's what's showing up on the spring scale. You may not be able to read it. I get about maybe 6.9. It's a shade less than 7 newtons, so I'm going to call it 6.9 newtons. And then I'm going to put this protractor here and measure the angle with respect to these axes, maybe this one, and count over, and I get approximately 45 degrees. Okay, so I have my data. I'll release this here and let it sort of rest on the board. And I will write the resultant of 6.9. Again, you're going to get your measurement, quote, in quotation marks, off the spreadsheet, and a 45-degree angle. Okay. Once again, I'm going to repeat the ratio calculations. I know you calculated this in centimeters, but to stay consistent, I want you to recreate that ratio with all the units and all that stuff here. Same thing with this 4.8. Convert these two to centimeter readings. And then draw the centimeters in the y direction, the centimeters in the x direction as accurately, as precisely as you can. Dotted lines, sketch the resultant and label it R. Measure that with your ruler, okay, right here, and then convert that centimeter value back to newtons and compare it to here. You could go back in the video and see how I did this first calculation if you get confused and you're not sure what to do. So you're just repeating all the calculations again, okay? And then now we are on step 16. We repeat the entire procedure again, but take the 500 grams that we have in the x direction and replace it with the 700 grams. Okay, so let's do that. Okay, this one stays 500 in the y, that 4 point whatever newtons. And this, to achieve 700 grams, what I'm going to simply do is add 200 onto that block. I got 500 and 200, giving me 700 grams. But before I start adding these forces through the string and with the drawings, I first have to get how many newtons that is on the spring scale. So I will lift that up more towards my line of sight, and I get, looks like 7.8 newtons. I'm sorry, 6.8 newtons. 6.8 newtons. Let me jot that down. So in the x direction, I now have 6.8 newtons. Again, you are going to look on the spreadsheet and get your own data. Okay, 500 grams here. It's the same as before, 4.9 newtons. So again, you're just going to, oh yeah, okay, get that off the spreadsheet. Now I have to add these with the strings again in the same manner as I already did twice. So let me move this out of the way. Get the 500 here. Okay. Oops. Extra 200. Okay. All right. So I have to get this to be on the low friction pulley here. This also on this low friction pulley. And I'm going to measure these two forces again using the spring scale. Okay, so I just put my finger through here and let the spring scale swivel and move it around until I take the pressure off my finger and support those two forces with the knot hovering right over the origin of the board. So there, now I have 6.8 newtons in the x direction coming from that hanging mass, and 4.9 newtons coming from the y direction hanging over this pulley. And those two forces, 6.8 and 4.9, add together on the spring scale, and I get approximately, let's see, I'm reading about 8.3 newtons right here, 8.3 newtons. The angle, again, I put my protractor here. Counting over from this axis here, I get about 55 degrees. 8.3 newtons, 55 degrees. So I'll jot those down. .3 newtons is the resultant. Again, Newton, 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 and 55 degrees. We need that little degree symbol, otherwise we lose a point. So now we're going to see if we can figure out this 8.3 from the diagram again. So we again convert this with a ratio. Don't skip any steps. Get all your units in here. A ratio of converting the 6.8. Now you're going to get 2 centimeters values. One in the y direction, and then this centimeter value in the x direction. Draw those arrowheads as accurately as you can. Make dotted lines. Sketch in that resultant nicely, cleanly with the ruler. Put nice arrowheads everywhere, as you saw here in this diagram, my nice arrowheads, my dotted lines, resultant. Measure that resultant in centimeters, and then perform another ratio calculation to convert that centimeter value back to newtons so we could compare it with that spring scale value. That is all the data for the lab. Okay, all the measurements, percent error. And then here we have some questions. Answer them as best as you can, and then when you're all done, like I said, there'll be 4 pages I want to see. The instructions you don't need to send back to me. I have those, right? So I don't need those. But what I need you to do is take photos of each of your sheets, well, in order, hopefully. Let's see. And, you know, submit them onto the stream as you're, and then also when you're taking photos, each of the photos, make sure you have a ruler somewhere, the ruler you use visible in the photo. So again, I could check the accuracy of your drawings by comparing it to the ruler. You don't have to have it right here. I'll just, you know, measure this and make sure that this measures the same amount on my screen as your answer. So that's the lab. 4 images, send them back to me, and then I'll grade them. Okay, well, that's the Adding Forces lab. Good luck with the analysis. By the way, it's not due at the end of this lab period. We'll be working on it in class the next lab period. So you have 2 lab periods because it's a pretty long lab to analyze it and turn it in. Okay, I hope you enjoyed, and I'll see you in the next lab.